This is lecture 10, so it's our penultimate lecture, the lecture before last, where we'll be talking about discrete time signal processing and the zTransform. So this is lecture 10 of a total of 11 lectures. So the last two lectures will be talking about the same thing, which is discrete time signal processing. So we'll be introducing zTransform today, and in our final lecture we'll look at some further and inverse zTransforms. And as I've said before, as we move on from week 5, everything seems to be getting a little bit easier, and I hope you'll notice that today's lecture and the next lecture are probably the easiest lectures of the whole semester, so not long to go. And just as a reminder, by the time you watch this lecture, you will probably already have sat your class test on the 14th of December, and that will have included contents from lectures 8 and 9. Now, the contents of lectures 10 and 11, these will be assessed in January. So as soon as you're back in the new year, there'll be an assessment of lectures 10 and 11. So I'll try to make sure you have lecture 11 recorded and available to you before Christmas. Okay, so quick recap from last time. So we introduced this idea of the Laplace transform last time, and we said, look, it looks very similar to a Fourier transform if you imagine S to be a complex frequency, and if you only consider the signal to be causal, i.e. starting at t equals 0, then the Laplace transform and the Fourier transform are virtually identical. And we introduced this idea of a transfer function as being the frequency domain version of the impulse response. And we said that we can write the output in terms of the input in the frequency domain in a similar way as how we would normally have done that in the frequency domain. And we mentioned how convolution in time is equivalent to multiplication in frequency, and we've done plenty of examples on this. And by now you should have completed a test about this. This week, rather than focus on continuous time signals and systems, we're going to be looking at discrete time systems. So we'll be looking at discrete time signal processing. We'll introduce the idea of a discrete time a discrete time block diagram, and we'll introduce the zTransform. So, remember we said a continuous time system takes a continuous time input and produces a continuous time output. And we find that output by convolving the impulse response with the input. Now, exactly the same applies if you have a discrete time system. It'll take a discrete time input and produce a discrete time output. And that output is also the convolution of the input and the impulse response. The only difference here is that rather than having h of t, we have h of n. And for h of t, we used the tool called a Laplace transform to find something called h of s. And we'll do something similar, but not the same, for h of n. So the question really is, what about discrete time systems? What's the equivalent of an impulse response for a discrete time system? What about the transfer function, h of s? So here we have h of t, and here we have h of s. But these only apply to discrete time systems. What's the equivalent for continuous time systems? So we can't use anything that involves integration for a discrete time system. So let's start by introducing an approximation that will take us from a continuous time system or a signal to a discrete time signal. And that will allow us to go from integration to summation. And I said lectures 10 and 11 will be easier. And part of the reason is because we're using simpler tools. We won't be using integrations. So we'll be introducing a discrete approximation. And in particular, we'll be looking at differentials. And we'll be approximating these using successive differences. So if you imagine that the derivative, first derivative of some continuous time signal x of t with respect to t, you can imagine that as being the difference of two consecutive samples, x of n minus x of n minus 1, divided by the time between them. So if you imagine you have some signal like that, and you have a sample here, sample here, sample there. So the time between samples is t. Let's say this is x of n minus 1, and that is x of n. Then subtracting the two and dividing by this time will give an approximation for the rate of change, or the gradient there. So this is an approximation. That's useful for situations where we have first, second, and higher differentials. We call this kind of equation where you have the output, and so this is the output, this is first derivative of the output, second derivative of the output, this is the input, and this is derivative of the input. We call this kind of equation a difference equation. Okay? This isn't a formula. Okay, just to be clear, I'm not presenting a formula. I'm simply presenting this as an example of a difference equation. So another difference equation could be this, where you have your output, you have previous output, you have current input, and you have previous inputs. When they're related together in a linear fashion, in this way, we call this a difference equation. So we can describe a discrete time system using this kind of difference equation. So this first example is an example of a differential equation. And this is for continuous time signals. Whereas for discrete time systems, we would use a difference equation. So notice this is a difference equation, these are differential equations. And difference equations are much simpler because, as you can see, they're linear. Whereas here, immediately when you have derivatives, they become non-linear unless you take them to the S domain. So this module, or this lecture, is about discrete time processing. So a discrete time signal processor relates the output to previous and present values of the input and the output. Okay, so if it was a non-causal system, you could have future values here, but for a causal system, these will be previous values. So using operations such as delays, addition and subtraction, scaling, you can create a relationship between the output and the input. So that's not the same as an impulse response. I'm not yet talking about impulse response. Right now, this is similar to lecture 8, where we would be talking about, or not even lecture 8, maybe lecture 7, where we would be talking about y of t as a function of x of t. For example, so this is how we used to talk about, or how we used to characterize continuous time signals before we introduced the idea of an impulse function. So I'm doing the same thing here. I'm relating the output to the input. The only difference is we're now talking about discrete time signals because we're talking about discrete time systems. So to represent these difference equations, so this kind of equation using these operations, we can represent these using block diagrams. So we use certain blocks. When we put a t, what we actually mean is a delay by t seconds, or by 1 second. So a t delay is a 1 second delay. Or you could replace the letter t with the number you want. So if I put a 1 here, that would mean a delay by 1 second. Okay, so that's our t blocks. You can also have addition. You can represent it like this or like that. If you wanted subtraction, you would put a minus sign there or a minus sign there. Okay, you wouldn't put a minus sign there, but some textbooks, some websites, some notations will put a minus sign there. But if you were to put a minus sign there, it really would be confusing. You wouldn't know if it's this minus this or the other way around. So the convention is always to have a plus in here or a summation. And strictly speaking, if you're adding two signals, you put summation, then you're adding the two signals. If you're adding a constant, you put a plus. But I'm happy either way. So that and that are both acceptable, even if you were to put B of n here, and if you were to put A here. Either way, these are the same. These are to add two signals. And to multiply two signals, you would simply put a multiplication symbol in a circle. And what we try to do is to use as few blocks as possible. That will give us the most efficient implementation. So, remember, the week before last we introduced this idea of a cascade, where we have two systems where the output of one is the input into the other, and we said for a linear time invariant system it doesn't matter whether you have one before the other. Okay, because the result is always the convolution of the two impulse responses. What we didn't really speak about was parallel combinations. A parallel combination is where the input splits and goes into each of these two systems, and then the result is added together. So in a parallel combination, that gives you an equivalent impulse response of the sum of the two impulse responses. So these are not the same. So back to this question. The question was, what's the equivalent of a Laplace transform in the discrete world? And this is where we introduce something called the zTransform. So say hello to the zTransform. Okay, it looks a little bit like a Laplace transform in the sense that it starts from 0 to infinity. You have your signal, and you have this new variable, z to the power minus n. So this will take our time domain signal and it'll move it to a new domain where your variable is, your independent variable is z. So look carefully at this. We're going to be using this a lot over the next 2 lectures. So x of z, that takes your time domain variable n, and it's converting it to discrete version of complex frequency. We integrate from 0 to infinity, and I'll show you in a second that this doesn't have to be the case. There are versions, so depending on whether you're looking at the unilateral or bilateral zTransform, that can be minus infinity or 0, but in this module we're looking at all signals being causal for this particular application. So that's your zTransform, and it's very similar to your Laplace transform. So the zTransform and the Laplace transform, if you like, are both transforms to take a time domain signal, whether it's continuous or discrete, and represent it in a new domain. So x of t, or if we look at h of t, that'll give you h of s, and h of n will give you h of z. The impulse response, we called it h of t when we were talking about continuous time signals and systems. We'll call it h of n when talking about discrete time signals and systems. And after carrying out the z or Laplace transform, the transfer function, which is the ratio of the output to the input, it was h of s for the continuous time signals and systems, it's now h of z. So just like h of s was y of s divided by x of s, h of z is y of z over x of z. So just as a reminder, when we were talking about signals, we spoke about continuous time signals, and we introduced the idea of a Fourier series for periodic signals and Fourier transform for periodic and non-periodic. But then I saved you the pain of studying about the discrete version of each. So just like there's a continuous time Fourier series, there's a discrete time Fourier series. Just like there's a continuous time Fourier transform, there's a discrete time Fourier transform. But I didn't include that in ELEC 270. But when looking at systems, I've included both. So we've looked at Laplace transform, now we're looking at the zTransform. And if you think of Laplace transform as the equivalent of a Fourier transform, where S is simply I omega or j omega, then you can think here of Z as being equal to e to the power I omega. That's why in the zTransform we don't have an exponential, we don't have an e, because it's included in this variable z. So, remember I said the limit for the integration for a bilateral, two-sided, bilateral just means two-sided. So for a two-sided zTransform, we integrate from minus infinity. But in this module, we will be looking at causal signals, and we'll be applying the zTransform from n equals 0. So that's how it will look like in this module. But if you do advanced signal processing next year, you're most likely going to be looking at bilateral rather than unilateral signals, and therefore you are most likely going to be considering the signal from n equals minus infinity. So, just like we have a table of Laplace transform pairs, there are tables for zTransform pairs, and you'll notice that these signals might look a little bit similar. So the summation is so easy, you often don't need to use the pairs. But the table is always there to use if you need it. So for example, very quick, easy example, if we take the simplest discrete time signal in the world, just a unit impulse. So if that was my signal, what's the zTransform? So when asking about the zTransform, what we're asking about is, so if we say x of n is delta, then the question is, what's x of z? Notice we're using uppercase X and n becomes z. So, several methods. Easiest method is just apply the definition. Now, definition might look really complex, but all we're actually doing is taking each value of x of n, in which in this case there's only one, and we're multiplying it times z to the minus 1. Now, for a discrete time signal, you can actually describe x naught as being 1. So this value here, if it was a continuous time signal, then that would be the area. But for a discrete time signal, or a discrete time version of the delta Dirac function, that is actually the area there. So all you're doing really is multiplying that times z to the power minus 0. So there you have 1 times z to the 0. And then because the signal actually looks like this, 0, 0, 0, 0, 0, 0, what you have is lots of zeros. So you've got 0 there, etc. So all values before and after this particular value is 0. Therefore, the zTransform of a unit impulse is simply 1. So that's one way of looking at it. Another way of looking at the same example is to simply look at the table, and there you have it. Even faster. Another example, this time we have the same signal, but this time it's shifted by one sample. So you've got your impulse there. Okay, for a discrete time signal, it might be easier to draw it that way. So you've got lots of zeros. Let me bring this a little closer. Then you've got zeros after. So applying the same definition, this time your 1 is right there. You've got lots of zeros that don't add up to anything. So all you have is 1 times z to the minus 1. Why is it z to the minus 1? Because that is always the same as that. So here, the only time when my signal is non-zero is when n equals 1. So I put a 1 there and a 1 there. So the zTransform of a delayed impulse is z to the power minus 1. What happens if we have a series of impulses? So let's look at something like this, where you have an impulse at 0, then 2, then 3, and then 4. After that, you've got a lot of zeros. And before that, there are also zeros. So, -1, 0, 1, 2, 3, 4, 5, 6. Okay, so same applies. If we're going to use the definition, then you simply take each of these values and you multiply each by the corresponding factor, z to the power minus n. And remember that this n is the same as that n. So you have 1 times z to the power 0, that's this one. And then 2 times z to the minus 1, that's this one. 3 times z to the minus 2, that's this one. And 4 times z to the minus 3, that's this one. So that would be your zTransform. So, did you notice that when we delayed our unit impulse, so remember when x of n was an impulse, the answer was, or the zTransform was simply 1. But when I delayed it by one sample, that gave us a zTransform of z to the power minus 1 times 1. So in general, whenever we delay by a samples, the corresponding zTransform will be multiplied by a factor of z to the minus a. So if you like, this is the time shift property of the zTransform. It reminds you of the time shift property of the Laplace transform. And before that, the time shift property of the Fourier transform. So Fourier, Laplace, and z-transforms. So if you have a signal x of n and it's delayed, then you have x of n minus 1, that's a delayed version of x of n. In the frequency domain, if you take x of z and you delay it, rather than using t, we use z to the minus 1. So try not to use t when talking about signals in the z domain. So z to the minus 1, this is a delay. Delay by one sample. So if you're to delay by 2 samples, it would be z to the minus 2. If you're delaying by a samples, it's z to the minus a. Final thing I wanted to introduce in this lecture is the idea of a transfer function, which is the ratio between the output and the input in the frequency domain. So this was from lecture 9. Okay, so this is for continuous time. The same applies for discrete time. So this time, our transfer function is the ratio of y of z over x of z. But it's the same idea. What we've done is replaced discrete time convolution with multiplication. So just as in the continuous time system would have x of t and x of s, y of t, y of s, h of t, h of s, here we have the same in n and z. So h of z is a z-transform of the impulse response. And exactly the same, we've spoken about cascade systems, and this is how they look like in the time domain. In the frequency domain, this convolution becomes multiplication. So you're allowed to multiply the transfer functions of cascaded systems. And you do that in the z domain just as you would in the s domain. Final couple of examples before we end the lecture. there's this idea of recursion or feedback. Now, if you have a discrete time process where the output is described in terms of the input, but also also including a contribution from a scaled and shifted version of the output. So this is the output, this is the input, but this is the previous output. So this is a difference equation. Okay, and what we're trying to do is, from this difference equation, to find the transfer function. So we're going from the difference equation to a transfer function. And it's actually quite easy. It's easier than it was when we were doing Laplace transforms, because all you need to do, it's a linear process, you can take a zTransform of each of these. So y of n, zTransform is y of z. X of n, zTransform is x of z. Slightly different when we get to y of n minus 1. It's y of z multiplied by z minus 1. That is because of the shift. And the a, because it's a linear operation, remains. Now, if you rearrange this, if we bring the y's together, you can divide by that, and it'll give you the ratio of the output to the input. Okay, so that actually gives you 1 over 1 minus a z to the minus 1. But if you multiply that by z over z, that'll give you that. And we tend to like it this way because we don't have any negative powers of z. This is also what you would expect to see in the zTransform table. So here we found the transfer function from a difference equation, simply by taking the zTransform of each of the terms. Another example. This time, instead of a difference equation, we have a block diagram. So we have a block diagram relating the input and the output. And the question is, find the transfer function. So you could either find the difference equation from the block diagram and then take the zTransform of all the terms, or you can somehow try to recreate the output in terms of the input just by following each of these branches. So there's 1, 2, 3, 4 branches. Follow those 4 branches. So if you follow this first branch, this is x of z. That 2 is a multiplication by 2. So after it comes out of that, we're adding to that, or if you look there, we're subtracting from that a delayed version. So this is a delayed version of x of z. So what you have here is x of z times z to the minus 1. What you have here is 2 times x of z. Now, if you follow this branch here, what you have here is 1/2 times y of z. Remember, this is feedback. The output is going back and being added with the input. So what you would have here would be that multiplied by your delay. So it'd be half y of z times z to the minus 1. Now, keeping in mind the minus signs there, all three of these are being added together. So you've got the first term, the second term, and the third term. Plus, minus, minus. Now, because what you want is the transfer function, you want to be able to divide y by x, so you bring all the y's to one side. So you would take this term here, bring it to the other side, take y of z as a common factor, so you'd say y of z times 1 plus half z to the minus 1 equals z to the minus 1 times, well, equals this basically. And then to find y of z divided by x of z, you'd simply divide both sides by x of z, then divide by that. That would give you that. And then to get rid of the negative powers, you would multiply by z over z. And that'll give it to you like that. And if you want to get rid of that half, you could multiply by 2 over 2. So if you were to multiply by 2 over 2, it would give you 4z minus 2 over 2z minus 1. So this, and this are all the same and correct, but we try to avoid negative powers in our transfer function. So that's how we would go from a block diagram to a transfer function. And there'll be many, many more questions and examples in the problem sheets this week. So that brings us to the end of lecture 10, where I've introduced the idea of discrete time signal processing, where we can use block diagrams and zTransforms. And this is, if you like, a gateway into lecture 11, where we'll talk about that in greater detail. So just as a reminder, we're right here at the very end of the module. We've just completed that, and we only have one more lecture to go. This is our final lecture. And just as a final reminder, your next class test is on the 4th of January. I'll send a reminder before that, but it'll be straight in the new year, so be ready for that. And that'll include the contents from lectures 10 and 11, both of which will be available to you before then. So I hope you found that useful. And from now until I next meet you, stay safe.